Okay, good morning, everybody. We're going to start with this warm-up. Today we're going to talk more about rates of change, specifically instantaneous rate of change, which is going to lead us right into our discussion about the derivative, which is related to the instantaneous rate of change. Okay, so the warm-up problem for today is talk about average rate of change. So try to dig back through your notes or dig back through your mind palace, find where you stored that information. Try out these two problems. I feel like I'm still struggling with some of the names on this side. We have McLaren, right? Kevin. Are you Chloe? Jordan. That's right, Jordan Slater. And then, you're not Caitlin, are you? Caitlin sits behind you. What's your name? Sorry? Hannah. Okay. So Jordan and Hannah, those were the ones that I couldn't quite remember. Okay, before we jump into the warm-up problems, I want to remind everyone we have an exam coming up. It's next Monday, which is, I think, what is today? Today's the 14th, so that'll be the 21st. I don't know why that came up. September 21. So I'll briefly explain what my plan is for that. I'm going to write a practice exam for you guys today. My goal is to have it to you by today, but latest by tomorrow. And what's on the practice exam will be Well, the goal of the practice exam is to give you problems which are similar in nature to the ones that you will see on the exam, but not necessarily similar in content. Okay, so what I mean by that is you'll get an idea on the practice exam of the types of questions that you'll see. It'll be a lot of explain your reasoning. It will be a lot of show your work very carefully and these sorts of things, because the exam that I'm going to give you guys is going to be take home, okay? So you'll have like 12 hours to do it. I'm not gonna write an exam that's gonna take 12 hours to do. It's gonna take like around an hour or so. And I will expect you to work on your own without any help from your book or online resources. I am undecided on whether I want to let you use your class notes or not, but I got a little bit more time to decide on that. I'll tell you on Wednesday whether I want you to use your notes or not. Any questions about the exam? Yes?
Just on chapter 1, right? Not what we're doing today.
It will cover everything that we do up until this Wednesday. So it will cover what we do today, and it will cover what we do on Wednesday.
We won't have class Friday?
We will have class on Friday. Friday will be a review.
Okay.
When you say we have 12 hours, do we like have to scan it in? Or like we just turn it into on that Wednesday?
No, I will expect you to scan your solutions as a PDF and submit them to Blackboard. Good question. Yes?
Are you gonna just post like something for us to print, or are you like handing it out?
I will post the page that I'll post will have the questions on it. Do you want me to leave enough space that you guys can do work on it in case you want to print it out? Okay, then I'll put plenty of space into the PDF. But yeah, basically I'll upload it at 9 a.m. on Monday. You guys will have all of Monday to do it. If you want to do it during class time, great. Otherwise, you can do it at your leisure, and then you have to submit it to me that day by 9 p.m. Is everybody clear on the exam stuff? Okay. If you think of any other questions, you can just email me or you can come talk to me in office hours. I have office hours today from 12 until 1. Link is on Blackboard. If you're concerned about the exam, come and talk to me then. Okay. If there's no other questions, pressing questions about the exam, then we'll do the warm-up problems. Okay, did anybody remember what this formula should be in number 1? Yeah, Mary?
F of B minus F of A over B minus A.
That's exactly right. So you guys might recognize that as the same formula that we use for finding the slope of a line. Can anyone tell me why that is? Yes, Yasmin?
Because for the average rate of change, we're just calculating like the average of 2 points, which is basically the line.
Yes, that's exactly right. So what Yasmin just said is that when we compute the average rate of change between 2 points, what we're really doing is computing the slope of the direct path between those 2 points, okay? So, for example, let's do x cubed. I'll do a drawing. Let me put that x's a little bit lower down. Okay, so what does x cubed look like? It looks like this on this side and like this on this side. Okay, so if here's 2 and here's 3, and those are the 2 points that we're supposed to find our average rate of change between. Okay, the way I'm going to compute this is So I'll go up to my point here, okay, there's my point number 1. Then I'll take 3 and I'll go up to the point which corresponds to 3. And then what I'll do is I'll draw a line which goes between these 2 points like this. Okay? And the slope of that line is equal to the average rate of change of the function in between these 2 points. Okay, that's what we learned before. Okay, so let's go ahead and use the formula that Mary provided for us. So, in our case, A is going to be 2 and B is going to be 3. So what we want to do is f of 3 minus f of 2 divided by 3 minus 2. So we just get 1 on the bottom. That's nice. And on the top, I'm going to plug these numbers into my function. Okay? So first comes 3 cubed. Then we have a minus sign, and then comes 2 cubed. So 3 cubed is 3 times 3 times 3, also known as 9 times 3. If we multiply those numbers together, we get 27, and then we'll have a minus sign, and we get 2 cubed is 8. So we get 19. Okay. That was just a review from the chapter where we talked about average rate of change. Okay. What we're going to do now is we're going to transition into talking about instantaneous rate of change. And before we start, what I'm going to do is really briefly look at this graph here. You know what? Let's just go with the notes. I'll come back to that graph and I'll draw some more pictures for us. I want you guys to have exposure to the ideas first. Okay, suppose we wanted to find the slope of a function at a specific point, x equals a, instead of between 2 points, x equals a and x equals b. So if we just wanted to find the slope of our function at a single point instead of taking it over an interval, that's what we're trying to do now. Okay, so there's a couple ways we can try, and the first way we want to try is using this method where we're just going to take the average rate of change and we're just going to say, okay, what if we just let a be equal to b, right? If we have a and b be the same number, then let's try our formula and see what we're going to get. Well, we know that a is equal to 2 and b is equal to 2. So what are we going to get? F of 2 minus f of 2 over 2 minus 2. And you might realize that this is going to give us 0 over 0. So the purpose of this being in here is to show you guys that we can't actually just plug in to the average rate of change function to get, or the average rate of change formula to get our instantaneous rate of change by taking a and b to just be the same point. We get 0 over 0, which is not defined. When I say not defined, I mean 0 over 0 could really be anything. Sometimes 0 over 0 will be infinity, sometimes 0 over 0 will be 0, sometimes it'll be 10 or negative pi. It really could be, it's anyone's guess what that means at this point. We can use more sophisticated techniques using limits to figure out what it actually means. But right now, what we have on our paper is meaningless to us. So we're going to have to try to develop some kind of more sophisticated technique for finding the instantaneous rate of change. Okay, so that's why did the calculation you performed in problem 3 not work? We got 0 over 0, which is undefined. Okay? Undefined. All right, let's try a different approach. So what we're going to do here is we're going to find the average rate of change between x equals 2 and x equals 3. We already did that part. Then we're going to find it between 2 and 2.1. And we're going to find it between 2 and 2.01 and then 2 and 2.001. Okay, so now, before we get started on that, I want to go back up to our drawing and point out what we're really going to be doing. Okay? I'm going to give myself a little bit more space here. You're just going to have to imagine that 3 is like all the way over here. Okay, so what we did in our original problem was compute the slope of this line right here. Okay? We want to know the slope right at this point right here. This is what we want. We tried just using a equals to b, and that didn't work. So now we're going to try something else. So this was step 1. Red was step 1. And now I'll draw in pink what step 2 is going to be. Step 2, we're going to move our point closer. Okay? And then we're going to try to compute the slope of this line like this. Okay? That was step 2. Step 3, we're going to move our point even closer and compute the slope of this line. That was step 3. Then we'll move our point even closer. That's step 4. And so on and so forth, okay? And as we keep moving this point closer and closer to the point where we want to find the instantaneous rate of change, the slope of these lines is also going to become closer and closer to the slope of the blue line, which is what I'm trying to find out. Okay, so hopefully, as we perform this process of step 1, step 2, step 3, step 4, we see a pattern. Okay? For example, if I saw that step 1 gave me a slope of 3, and then step 2 gave me a slope of 2.5, and then I got 2.1, and then I got 2.01, it would reason to say that the slope of the line at the point is approaching 2, right? If our slopes are getting closer and closer and closer and closer to 2 as we move ourselves very close to that point, then we can conclude that the slope at that point is actually 2. So let's actually do that process algebraically. What we're going to do is we're just going to use our average rate of change formula, okay? So first we did between x equals 2 and x equals 3. I think we already did that. We got the slope was something like 19. Okay, so now we're going to do part B. Okay, so I'm just going to do b is equal to 2.1 and a is equal to 2. So what do we get? 2.1 cubed minus 2 cubed divided by 2.1 minus 2 is just 0.1. Okay. And if you do that, you get something like 9.261 minus 8 over 0.1, which is equal to 12.61, something like that. Okay. Now let's do it again using step C. Okay, we're going to use an even smaller number that's closer to 2. 2.01 cubed minus 2 cubed divided by 0.01. And notice we have two things changing here. The numerator is changing because we're plugging in 2.01. And the denominator is also changing because the denominator, remember, is the difference between b and a. So if we change b, the denominator is also changing. So we have the top getting smaller, and we also have the bottom getting smaller. But what we're hoping to see is that the ratio is consistently showing us a pattern that the ratio is approaching some number. Okay, so if we plug this in and calculate it out, we get 12.0601. Okay, starting to see a pattern. If we do the next step, 2.001 cubed minus 2 cubed all over 0.001, we get 12.006001. So it started at 19, then we got 12.61, 12.0601, 12.006001. Stands to reason if we took it one step further, you know, here we had 1 0 in between, here we had 2 zeros in between. We're going to keep getting more and more zeros filling out our thing until it looks almost identical to what number? 12, that's right. So based on our results in problem number 5, what do we think the slope of f of x equals x cubed at x equals 2 is? 12. That's my guess, based on what the data is showing me. Has anybody here done pre-calculus or even a little bit of calculus in high school? You guys might recognize this is pretty similar to what you would call a limit, right? Yeah, we don't actually teach limits in this course for some reason, which I don't fully agree with. But this is basically that process written down in a more complicated way. So basically what we're doing here is a limit. Any questions on how we're performing this process or on the drawing that I did up at the top? How I was doing those slopes as we're getting closer and closer to the point? Okay. So based on our observations in problem 3 to 6, let's try to come up with a method for computing the slope of a function y equals f of t at a point x equals a. Okay, who wants to help me come up with a formal algorithm here for what we're going to do to find the slope of a function at this point x equals a? So what I'm looking for is for someone to give me directions on how I'm to proceed if I have some function and I want to find the slope of that function at some point a.
Well, we need the formula should be y equals mx plus b, right?
Say again?
The format should be in y equals mx plus b, right?
Well, that's an excellent point, actually. We don't have to have a line. Okay, so our function that we're finding the slope of can be a curve. And that's why this whole problem is so tricky, because we want to find the slope of something that's not a line. We want to find the slope of something that's a curve. And the slope of a curve is constantly changing every which way, right? Sometimes we're rising very quickly, sometimes we're rising more slowly. And so we don't want to use the formula y equals mx plus b to compute the slope of these lines. Well, we don't want to use the formula y equals mx plus b to compute the slope of a curve, because y equals mx plus b is the equation for a line. Thank you for bringing that up. So in terms of directions for doing this, will anybody help me out? Yasmin?
You draw like how you did in the picture. I think it's called a tangent line, like
Mm-hmm.
on the point where you're trying to find it, so that you can
Sure. We can draw a tangent line. Whoops. That's getting ahead of ourselves a little bit in terms of the terminology, but that's exactly what it is. We call this red line a tangent line, and what it means for something to be a tangent line is that it's defined to be the line which comes in and just barely kisses our graph at one single point and then shoots off forever. Okay? That's what it means for it to be a tangent line. And the instantaneous rate of change corresponds to the slope of the tangent line. Okay? So if you imagine, if we were to move this red point to the left and to the right and we were to follow it along our graph, we might get many different tangent lines, right, as we go along. Here's another one. Down here we could have another one. These are all tangent lines. And the process is to kind of put our flat line on our graph, and as we move around, it's going to change its slope if we move it to different points that are on the graph. That's basically what's going on with the tangent line. Okay. In terms of an actual algorithm, here's what I think we should put down. We should put something like compute the average rate of change at or between A and A plus 1, A and A plus 0.1, A and A plus 0.01, dot, dot, dot. Then try to recognize a pattern. Okay, I think that's what we should do.
What does it say A and T1 or dot?
A and A plus 1 is
Oh.
what that is supposed to say.
Sorry.
I make my pluses a little bit more neat. Always appreciate people calling me out on my horrible handwriting.
Sorry, but
Okay, so that's what I'm looking for in terms of like an algorithm. An algorithm is just a set of instructions. It's like what I would find in a cookbook if I was trying to cook up the instantaneous rate of change. It would tell me exactly what I need to do in order to get it. Okay, all right. So let's talk about this paragraph down here. This is kind of important. This is what I would typically write this out in class, but we'll go through it slowly. The instantaneous rate of change of f at a. Okay, so that's what we've been calculating so far. Also called the rate of change of f at a. Okay, so sometimes we drop the word instantaneous and we just say the rate of change at a. If I say at a, well, a is just one point in our domain, so that's how you know I'm talking about the instantaneous rate of change if I just say rate of change at a. Is defined to be the average rate of change of f as the interval around a gets shorter and shorter. Okay, what does that mean? If this is a here, then I'm going to take an interval which goes from a to maybe a plus 1, and then I'll move my interval even smaller, a to a plus a half or something like that, and then I'll move my interval even smaller. It'll just be a to something really close to a, and so all of these guys are getting closer and closer and closer and closer. Okay, so that's what this definition says. It says that the instantaneous rate of change is defined to be the average rate of change as f as the interval around a gets shorter and shorter. Okay, so this is actually the definition that we're using. If you've seen calculus before, this is not going to be the usual definition that you have seen. So this should be new for pretty much everybody. Okay. The instantaneous rate of change of f at a is equal to the slope of f at a. What that sentence means is sometimes we use these two terms interchangeably. Sometimes I'll ask the class, what is the instantaneous rate of change of x cubed at x equals 2? Sometimes I might say, what is the slope of x cubed at x equals 2? Okay, these two things mean the same thing. Okay. Are there any questions about this terminology? Basically, the takeaway from this green highlighted part is instantaneous rate of change at a means the same thing as rate of change at a means the same thing as slope of the function at a. That's what the green part really is saying. Okay, let's have some more practice. The quantity in milligrams of a drug in the blood at time t in minutes is given by g of t equals 25 times 0.8 to the power t. First, let me ask, what kind of function is g of t equals 25 times 0.8 to the power t? Yes, Sri?
Annual,
Sorry?
annual interest.
We use these types of equations to model interest. But I'm looking for a more general term. Yes, Alice?
Exponential.
Exponential is the term we want to use here. Okay, exponential. And is this going to represent exponential growth or exponential decay? What do we think? I'm hearing decay. I think decay is what it's going to be. How do you know it's decay? Whoever said that? Somebody. Yeah, Dylan?
It would be like 1.80 if it was growth.
Exactly. I think what you're expressing here is that since 0.8 is less than 1, this tells us we have exponential decay. You could also have just inferred that from the context of the problem. If we put a drug into our system, what happens to it over time? It goes away, right? It doesn't continue to become more and more like present in our system, thankfully. Okay. So use the rule we wrote down in problem 7. What was problem 7? Okay, the problem immediately before. Okay, so we're going to use this algorithm to estimate the rate of change of the quantity at t equals 3 and interpret our answer. Okay, so I'm just going to do the steps in the order that I have them. The first step is to compute the average rate of change between a and a plus 1. Well, in the context of the problem, what should I choose to be my a?
0.8.
Not 0.8. Now that's a great point, actually, because this is a little bit confusing. In the exponential chapter, we talked about this number here as being our a for our formula, right? Right now, we're treating this formula as separate from our problem. So the a that I'm referring to in number 7 here, where I give directions, is the point x equals a, okay, where I want to find the instantaneous rate of change. In the problem, the time at which they want us to find the instantaneous rate of change is t equals 3. So, first of all, a equals 3. We want to compute average rate of change between 3 and 3 plus 1, which is 4. Okay? We're just going to use our formula, okay? 25 times 0.8 to the power 4 minus 25 times 0.8 to the power 3, all divided by 4 minus 3 is 1, gives us, if we type it in, negative 2.56, something like that. Negative 2.56. Add a page in here and get the paper fixed. Okay, step 2 said compute the average rate of change between A and A plus 0.1. All right. So average rate of change between 3 and 3.1. We plug into our formula, we get 25 times 0.8 to the power 3.1 minus 25 times 0.8 to the power 3, and we divide all of that by 0.1, the difference between 3.1 and 3. If we plug that into our calculator, we get something like negative 2.82461, something like that. Dot, dot, dot. Can't remember if that was a repeating decimal or not.
So where did you get that 3.1 from?
Great question. 3.1 came from our directions in part 7. So the first direction, let me highlight in orange. The first direction was to compute the average rate of change between A and A plus 1. So that's why we used 3 and 4 in our first step. The second step says compute the average rate of change between A and A plus 0.1. Well, A is 3, so 3 plus 0.1 is 3.1. That's how I found my second part there. Okay, so I computed the average rate of change between those two numbers. And now, guess what? I'm going to let this second number become even closer to 3. I'm just going to add 0.01 this time. So my third step, find the average rate of change between 3 and 3.01. And we get something like, well, we're going to get 25 times 0.8 to the power 3.01 minus 25 times 0.8 to the power 3, all divided by 0.01. And if we plug that into our calculators, we would get negative 2.85305. Okay, something like that. So now we've done steps 1, 2, and 3. Step 4 here is then try to recognize, wow, that's a really bad word there. I did not write that properly, did I? Then try to recognize a pattern, okay? So we've got 3 steps and we're trying to recognize a pattern. So first I had negative 2.56, then I had negative 2.82, and I had negative 2.85305. If I took it one step further and did between 3 and 3.001, I would get something like negative 2.85592. What do we think that this is getting close to as I go along? We got negative 2.82, negative 2.853, negative 2.8559. If I were to guess what this is getting close to. I think we're capping out at around negative 2.86. Okay, looks like we are getting close to negative 2.86. Yes?
Let's say like I thought it was negative 2.9, like would I get it wrong?
Let's see what the problem says. Okay, so that really comes down to what the problem states, okay? The problem states the quantity in milligrams of a drug in the blood at time t, use your algorithm to estimate the rate of change, okay, the instantaneous rate of change. So there was a little bit of guesswork involved there at the end as to where we're actually heading. Okay, the reason that I said 2.86 was if we had one jump which only went from 85305 to 85592, as I keep going with this process, the change between this number and the next one will be even less than it was between the last two, right? It's going to get closer and closer and closer, and each step that we take is going to give us diminishing returns in terms of getting really close to our number. So that's why I said negative 2.86. That just comes from experience of computing these things many, many times. If you said something like negative 2.9, that would still, I think, be within the realm of a reasonable answer, because we're asking for an estimate here, okay? An estimate's not going to be exactly right, okay? I guarantee you that negative 2.86 is not exactly the answer, okay? So if you said negative 2.9, my inclination would be to give you full points on the problem. If you said something like 3.5, I'd be wondering how you got that. Does that sound like a fair way of grading a problem like this? That seems fair to me. Okay. Any other questions about how we applied this algorithm to this problem? Yes?
I was just wondering, is this like a general algorithm that you can use for these problems like all the time?
Yeah, definitely. I mean, that's the hope anyways, right? It's not the only way that we could have done it. We could have used, for example, different numbers in 1, 2, and 3, just as long as we're getting closer and closer. Or we could have done a minus 1 and a minus 0.1, a minus 0.01. That's also getting closer and closer. That would have been all right as well. So it's not the unique way of doing a problem like this, but for now, until we learn how to use derivatives, this is the penultimate way to compute the instantaneous rate of change. Does that answer your question? Any other questions? Okay. Later on, we'll learn an easier way of computing these things using derivatives. By easier, I mean it's going to take a lot of work to build the derivative as a concept. Once we have it, it will make things more convenient. Okay, the derivative of f at a, written f prime of a, so this is a preview for next time, is defined to be the instantaneous rate of change of f at a, at the point a. Okay, that's what we call the derivative. Okay, what we're going to learn later is much more convenient ways of computing it than what we've done today. Okay, so what we just did was compute the derivative of g of t equals 25 times 0.8 to the power t. We computed the derivative of that function at t equals 3. Okay? So, all of these things are equivalent. We can say the instantaneous rate of change of f at t equals a, or the slope of f at t equals a, or f prime of a, or the rate of change of f at a. All of those things mean the same thing. I'll put a parenthesis around this instantaneous here because it's not, we don't always write that. Okay. We'll do number 9 and then we'll be done for today. Well, maybe we all have time for 10. We'll see. So we're supposed to graph f of x equals x squared on our calculator. We don't need a calculator to do that. We can just draw it. It looks something like, let's see if I can do this real good. That. Okay, and we want to determine whether the following quantities are positive, negative, or 0. F prime of 1, remember the derivative means instantaneous rate of change at whatever point is in our parentheses. Okay? So, with red here, I'm going to draw what this really means. What f prime of 1 means is if I go to the point 1 and I compute the instantaneous rate of change, which Yasmin kindly explained for us is actually the slope of the tangent line, right? This slope here. The question is asking, if I compute the slope of that line, is it a positive number or a negative number? What do we think? It's positive, right? Why is it positive? Because we're increasing. We're going up. Remember, we read this as left to right. If I was a person here walking in this direction, I'd be walking uphill, right? I'm increasing. Okay? So that's how we know that this should be greater than 0. Okay, how about f prime of negative 1? We'll do that with a different color. Purple, maybe. Yeah, we're going to see a pattern showing up real quick here. Now we're decreasing, meaning less than 0. F prime of 2, well, that's just further out. We're going to be increasing even more drastically. So still greater than 0. How about f prime of 0? Well, what would my tangent line look like right at this point? Well, I shouldn't use such a dark color. Let's use pink. What would my tangent line look like right at that point there? Avit? Exactly. It's going to be a horizontal line. It's going to be, in fact, it's going to be this line. Right? What is the slope of that line? 0. Okay, and f prime of negative 2, do we even need to draw the line? What do we think? Positive or negative? Negative. Okay. Which is larger, f prime of 1 or f prime of 2? What do we think? 2. Can you explain your reasoning? Why we think 2 is, f prime of 2 is going to be larger than f prime of 1? Yes, Abhi?
It has like more of a slope from 0 to 2 than 0 to 1.
Yes, that's exactly right. The slope is more intense, so to speak, right? If I was walking uphill, I would much rather walk up the red hill than walk up the green hill. It's a very steep, right? Steepness indicates magnitude in the slope, okay? The more steep it is, the higher the magnitude. So our answer is that f prime of 2 is going to be the larger one. All right, last thing, which is larger, f prime of -2 or f prime of -1?
Negative 1.
-1, that's right. Because if we were to draw in the other line, what would it look like? Look something like this. And while this has a greater magnitude slope, it's really more negative. So if I were to draw it on the number line, and here's 0, the red one would show up somewhere here, and the purple one would show up somewhere here. Since it's further to the right, we say that it's larger. Okay, that's it for today. If you have extra questions, you can stay after class, or I have office hours today at noon. Please come if you need help, or if you have been saying on the exit slips that you need more help.
Virtual or
Yes, virtual. The link is on Blackboard.
Well, is this the last? Oh, no, there's the last problem. Is Kenneth? This is the only last problem. This has the only problem left. Okay, on this notes.
Number 10, you mean?
Yeah. How you?
Yeah, sure. We could do number 10 if you want to hang out after class.
Yeah.
Yep. Have a good one, everybody. Mhm. Did you have a question about something?
Yeah, so for C, what are we talking about with the line?
Okay, yeah, probably that was a little bit weird to throw in there right at the end. Okay, so let me erase the line. When we say what is larger between f prime of -2 and f prime of -1, what I mean is, if I look at the slope of the red line as opposed to the slope of the purple line, the question is, which number, being the slope of these lines, is going to be larger? Okay? The slope of the red line might be something like -4, and the slope of the purple line might be something like -2. Okay? My point with the number line was just to say that we need to know that -2 is a larger number than -4. Some students who haven't done inequalities in a long time tend to say, aha, 4 is a bigger number than 2, therefore -4 is larger than -2. It's not the case. -2 is a larger number than -4. That's what I was trying to explain with the line. Okay, did you have a question, Ashlyn, or you want to see the last one?
I had a question about the continue this one first.
Let's take the question first, and then I'll do the last problem.
Okay, awesome. So on continuous interest.
Oh, okay, continuous interest. All right, we're gonna do this problem first, and then we'll go back to continuous interest. Okay, so suppose we throw a grapefruit straight upward into the air. The following table gives its height y at a time t. Why is it impossible to exactly determine the instantaneous velocity of the grapefruit at t equals 1 using only this table? Okay, the reason that it's impossible using just this table is we're given an incomplete set of data. Okay, so here's 0, 1, 2, 3, 4, 5, 6. So we know at 0 we're 6, at 1 we're 90, at 2 we're 142, at what have I done here? Sorry. 6, 90, 142, 162, 150, 106. 106, and then 6, 30, something like this. Why does that happen? Okay, So our graph looks something like this. And they're asking us to find the instantaneous velocity of the grapefruit. In other words, the instantaneous rate of change at t equals 1. So at this point, we'd like to draw a tangent line to this graph. And they're asking us why we can't do it exactly. The reason is we don't really know what the function looks like between these 2 points. We can infer that it probably looks like this. That's one case. But what if it looked something like this? That could also be a way to fill in those lines, right? So because I don't know what the actual function looks like, I'm just given these data points, okay?
So we're only given the data points.
Exactly. I don't actually know what the instantaneous rate of change is at that point. Okay, so that's why it's impossible to determine it exactly. Given the information we have, we can make our best estimate. Okay? Here's how I'm going to make my best estimate. Okay? If you imagine our graph looking something like this, what I'm going to do to try to compute the slope of this line, which goes through here like this, is I'm going to take the average of 2 different lines. One line which goes through okay, let me redo that. There we go. No. Come on, cooperate. Well, this line, and I'm going to also compute the slope of this blue line, and then I'm going to take the average of those 2 slopes to try to figure out what the slope of the purple line in between them should be. Okay? So how do I do that? I'll do average rate of change between 1 and 2, and then I'll do average rate of change between 0 and 1, and then I'll average them. So I'll do f of b minus f of a, 142 minus 90, all divided by 1. What is that, 52? 52. And then the other one will be between 0 and 1. We went 90 minus 6 over 1 equals 84. I think if we average them, we do 52 plus 84 divided by 2. 52 plus 84, that's 136. Divided by 2 is equal to 68. So that's one way that we can try to estimate. Now, this is not by any means going to be exact. In fact, it could be horribly wrong if our function looked like the pink one that I drew before. It's going to be all messed up. But it's as good as we can do with the information we have. And we can say, well, the most likely outcome is that these points are points on a parabola. And if we know that, then we can get pretty close to the slope. But like I said, it's really just a guess. Okay. Your problem was on continuous interest?
Yes.
I think so.
Do you remember what section that was? Yeah, no problem, Sri.
I think it was the second division. Because the third was
Okay.
like halfway from double.
Got it, so 1.8. All right. Wait, is this it? What is this? No, this is not it. Should have been 1.7. There it is. Okay, here we go. Annual versus continuous interest. What problem was it again?
3.
So this 30% decrease over a period of 10 years problem?
Yeah.
Okay, sweet. We can redo it.
I just got really tripped up on the part where you're looking at P of T1 equals P not A T1, and then how you use all of that to compute the answer.
Yeah. Can you verbalize what's confusing about this problem?
I just don't know necessarily the steps at which you implement all of that. Like P of T1 equals P not A
Mhm.
A to the T1.
Sure.
P to T2.
Okay. So my initial investment we usually write this as P naught. I think the confusing part of this problem is we don't know how much money we initially invest. So we do the best we can by just representing it by a letter. We'll use P naught. After 10 years, my question to you is, how much do we have left? If it decreased by 30%, say I told you P naught was $10,000. Could you tell me how much I have after 10 years?
Wouldn't you just decrease it by 30%?
Yes. Yes. So what would I get if I did that?
You would have 70% of whatever 10,000 is.
Yes. How would you
7,000.
Yes, so 7,000. That's exactly right. So if you took the number 10,000 and you wanted to get the number 7,000, what would you do to 10,000 to get that number? If you were to type it in on your calculator, you'd do 10,000 and then what?
Times 0.3? I don't.
You're close, you're close. Times not 0.3, but 0.7. 0.7, okay? So 70% of P naught is 0.7 times P naught. Okay? So if our initial investment's P naught, we just want to multiply by 0.7 to get what we got. Okay, so we know after 10 years we have 0.7 P naught. So what is this telling us? This is telling us we have 2 points. If I have my initial investment, what's time?
10 years.
T equals, at the initial investment, T is equal to what? 0. And after 10 years, T is equal to?
10.
Okay, so we can think of this as giving us 2 points on a graph, right? The first point is 0, comma, P naught. And the second point is 10, comma, 0.7 P naught, right? Okay. We know that this equation obeys certain rules. It's annual percent interest, okay? So we know it should look something like this. We should have P of T, right, is equal to P naught times A to the power T, okay? Our goal here is to figure out what A is. So all I'm going to do is plug this point into this formula. Okay? So this left thing, 10 here, that's going to go wherever I see a T, right? What about 0.7 P naught? Where am I going to plug that in?
Where P naught stands.
Not where P naught stands. Remember, this is the point T, comma, P of T. Right? It's after I plug 10 in for T here, I'll get this thing. Right? That's what this ordered pair is kind of representing.
Okay. Well, we did this
It does look different. I'm just trying to give you a different perspective on it. I think...
So.
Yeah, we can do it the other way.
No, no, it's okay. I was just making sure that it copied it down initially correctly. So.
Yeah, so what I tried to write down initially was a general way to do this at any time, okay? So the information that's encoded in this point here is P of 10 equals 0.7 P naught. And the information that's encoded in here is P of 0 equals P naught. Okay? So when I first wrote this down, I think I wrote something like P of T2 equals P2 or something like that, and then P of T1 equals P1. And then I said what you should do is divide those two things.
Yeah, so in the notes it was P naught A to T2 divided by A of T1 equals 0.7 P naught A
Sure.
to T1.
So what I really wrote here instead was actually I wrote P naught times A to the T2 and P naught times A to the T1. I think it's what I wrote down here is a way to generally compute it if you just know information at two different times. What I'm plugging in right now is kind of an easier version of that general form where I'm sort of using the fact that we have this 0.0 comma P naught. That's sort of convenient that we know what P naught is. So let me really quickly finish it my way, and then I'll talk more about the general way.
Okay.
So we know from this green thing here, 10 comma 0.7 P naught, what that says is if we take this formula, which is written on the left-hand side, and we plug in T, what pops out is 0.7 P naught. So the way I'm going to plug it into this formula is 0.7 P naught goes on the left-hand side. If I plug in 10 for T. So on the right-hand side, I get P naught times A to the power 10. Okay, does that feel okay? All right, now do you agree with me that you can cancel these P naughts?
Yes.
And if I have A to the power 10 equals 0.7, do you know how to figure out what A is?
Would it be 0.7 to the 1 over 10?
Exactly, 0.7 to the power 1 over 10. So that's how we would do that.
Okay.
Let me create an extra page. I'll go down here and I'll explain what I was talking about before. Okay. If I know three things, P of T equals P naught A to the power T. If I know P of T2, now this is a very specific time now. So this is just my formula. A to the power T2 some number. If I have this information, okay, so I have my formula, and they tell me that P of T2 is equal to some number, and P of T1 is equal to some number, I can figure out what A is using this method. Let me rewrite these numbers. I'm going to write them as a specific number. This one's going to be A, and this one's going to be B. So can you just remember that A and B are placeholders for some number? Okay, so in the formula, they might tell us P of 30 is equal to 200, and P of 10 is equal to 17. So 317 would be A and B, and then T2 and T1 would be 30 and 10. Okay, so the way I can find A not big A, if A, B, T1, T2 are known. I do not need to know what P naught is. Okay. I'm going to take these two equations and divide them. On one side, I'll get A over B. On the other side, I will get P naught A to the power T2 over P naught A to the power T1. Do you agree with me that the P naughts cancel?
Yes.
That's why we don't need to know what P naught is. The left-hand side is just numbers, right? And the right-hand side, I have A to some number divided by A to some number. Can I write that as a single power? I can write it as A over B is equal to A to what power?
It would be A to the power of 1 over T2 over T1.
You're on the right track. You gotta remember our exponent rules. If I have x to the fourth divided by x squared, what do I get?
X squared.
X squared. What did you do to get that? You took these two numbers and did what to them?
Subtract.
That's right. So if I have T2 and T1, what do I do with them?
Subtract.
So what should the power be?
So A to T2 minus T1.
That's right. You had it in you. You just needed to see it in a more familiar form. You can always write that down if you can't remember the rule. You can write it down in a way that looks more familiar to you so that you can figure out what the rule is. Okay, so this is the thing. We know that A and B are numbers, right? T2 and T1 are numbers, right? So this could be something like 300 over 17 equals A to the power 11. And what would you do? You would just take the 11th root of both sides, right? You'd set A equal to 300 over 17 to the power 1 over whatever that number was. 11, right? So in the general case, we would get A is equal to A over B to the power, what should my power be?
Would it be 1 over T2 minus T1?
That's right. Exactly. So that's what I was trying to tell you guys during that problem. Was I was trying to give you this very general information about like this method, which I wrote down here, can be applied to any problem of this kind.
Okay.
If we know the value at some later time versus some earlier time, or if we even just know how much it's decreased, then we can apply this method and figure out what A is.
And is that only for annual, or can that also be applied to continuous?
You can absolutely use it for continuous. The only difference here is that here where we have A and A, instead we would have e to the r and e to the r. Okay? So when you ultimately find out A, instead of finding out A, you would really actually find out e to the r. Okay? And so then you would have to do one more step. You would have to do r is equal to the ln of the right-hand side. Like that. If you wanted to find out what r was. In our case, we found out what A was. If we wanted to find out what the rate was from A, we would take A minus 1, right?
Okay. All right.
Yeah, so if you have continuous, you can do the same method. You just have to be a little bit more careful with the fact that you have e to the power r floating around. But you can just basically stick it in wherever you see an A, and it should work out.
Okay. Makes sense.
Yep.
Appreciate it.
Yeah, no problem.